All right, ladies and gentlemen, class recording has started. So, on Tuesday of this week, we introduced ways that we can describe periodic motion and the waves that are created by periodic motion. So, I gave you this example, right, of the pendulums. The pendulums are swinging back and forth, right, and we use those to talk about the different concepts of period and frequency and things that are related to repeated disturbances. Up on the board is a list of your objectives from Tuesday. We didn't get through all of them, but the first one deals with defining 4 terms. There's only 3 up there, and I should add the 4th one. And that 4th one should be period. So period, frequency, wavelength, and then the 4th one is amplitude. We haven't gotten amplitude yet. We'll do that today. To start us off for today, I'm going to show you a picture of a wave. It's going to have some information, and I want you to identify a couple things about that wave based on our definition from Tuesday and the information that's on the picture. Okay? Don't yell out the answer in your head. Right? Think, don't yell, so that everybody has a chance to kind of go over it. And we'll start with this picture. All right. Wavelength of this wave is 1.5 meters. Okay? So, as its name suggests, the wavelength is the length of one wave. And in your notes, we said there were a couple ways to define that. It says, your notes say wavelength is the distance between the same spot on 2 consecutive waves. So we said there's a couple ways we can define that. First, we can measure this distance. That's the distance from what to what? Crest to crest. Or we can measure this distance and just trough to trough. Okay? But something that we have to keep in mind, measuring that might be easier for certain waves than other waves. In this picture, the wave or the measurement of this 6 meters down here at the bottom doesn't start at a crest or a trough. It starts in the middle. But remember, a wave is a complete cycle of motion. So if we talk about a wave here in this picture, this one starts here, it goes up like this to a crest, and it comes back to the rest position, but that's not a full wave, right? That's only half of a wave. We haven't gone through the whole cycle. So a 1 full wave would take you back down here to the trough, and then back to its original starting position. Even though it passes through the middle, at this point, that's not a full wave. So in this picture, how many waves are there? Total. 4. There are 4 waves in that picture total. Okay? Good there? All right, next question. This wave has a period of 0.25 seconds. The frequency of this wave is, use your notes, think about it, don't just yell at the answer. All right. Frequency of this wave is 4 hertz. Okay? No, go ahead. Are you good with that or no? Okay. So, we talked about.
What are you?
Sharpen his pencil. He did pass a pencil sharpener on the way. That's all right. All right. So we said that period is a time, right? It's a time for one way. You can just go back to that. Believe me, doing a whole lap around the outside of the room is much more disruptive than just that. So. All right. Period is a time. It's a time for one wave. But what does frequency tell you? The number, right? Frequency is a counting thing. Specifically, Rhea, the number in what? Well, yes, the number of cycles in 1 second. Okay? So we're talking about how many cycles or how many waves happen every second. No, go ahead.
So, are you counting like it's half?
Now, remember we said that a wave is a full cycle. So here, that's one wave, right? So it's saying here that when it says that that wave has a period of 0.25 seconds, it takes 0.25 seconds for that to happen, okay? And then we can then extrapolate and go, okay, if it takes 0.25 seconds for this to happen, in 1 second, 4 of those would happen. And that's why the frequency is 4 hertz. Okay? So remember that hertz, right? Hertz is a unit that we use to represent a counting thing. So saying 4 hertz is the same as saying 4 waves every 1 second. That's what hertz means. Okay? Catherine, go ahead.
But how does the period of 0.25 seconds, how does that help you figure out the frequency?
Okay, so we said first we could do it just by that reasoning, right? That if the period is 0.25, that's the time for one wave. And if frequency is how many waves happen every second, we can go, okay, well, if one of them takes 0.25, the rest of them take 4. There's 4 every second, okay? But another way we can do it, right, is that
Count the waves?
you could count the waves, right? But you don't know specifically how much time this is. I didn't really tell you that.
Yeah.
But the other thing we can do is we said that if each wave gets shorter or takes less time, how many waves will there be every second? If each wave takes a smaller amount of time, how many waves will there end up being? More waves. That's what kind of relationship? Inverse relationship. So we said that we can figure out the frequency of the wave by taking 1 over the period. If we know the period, we can take 1 over that period and get the frequency. We can also go the other way. If we know the frequency, we can go 1 over the frequency, and that will give us the period of each, or the period of each way, one way.
Okay. Wait, so if you plug into the formula for frequency,
Yep.
it'd be 1 over 0.25?
Right. So it's 1 divided by 1.25, right? Or 1 divided by 1/4, right? Does that make sense?
Yeah.
And you have a complex fraction, but that simplifies into 4. All right, good there. Okay, let's pick it up from there at here and there. All right, the next term that we use to describe the wave and the properties of that wave is the amplitude. And the amplitude, we use the capital letter A. By definition, the amplitude is the maximum displacement of the medium from rest position. The maximum displacement of the medium from rest position.
You need to make bigger lines. I apologize.
I try to keep it on one page. All right.
Do you want to think about us?
Think about the environment. So, it's all about you guys. All right.
Wait. I was trying to fit it all. No, I wrote the wrong line.
So, hey, let's go back to this pendulum. Here this pendulum is rest position, right? It's the slowest position, it's not moving anywhere. To get the disturbance started, I have to do what to that?
Work.
Work, right? And work requires two things.
Movement or energy.
Force and
Force.
movement, distance, right? So, I apply a force, I move that out to a certain distance, and this starts, right? How do I make it go higher?
More force. More work.
More work, right? Could be more force, could be more distance, right? But more or both, right? So more work, right? What happens when I do more work on the pendulum? It swings higher, right? It has a greater what? Amplitude. So what does the amplitude tell you about a mechanical wave?
It's that'll become faster and for sound.
Not necessarily faster.
Stronger.
For sound, it would be what? It would be louder, but not necessarily a different. No, not higher. That's something different. Okay. It tells you about the energy, right? So the amplitude of a wave. The bigger the amplitude, the more energy that wave carries. That relates to volume, not to pitch.
Okay, what does
Pitch is frequency.
Oh, okay.
So remember we talked about the music. We talked about musical notes the other day, right? That piano string vibrates a certain number of times, and that's the note that it plays. But if it vibrates that same number of times, but it vibrates more, it's the same note, but it's louder. Okay? So amplitude deals with energy. Okay? Good there. Okay. Next. Oop. Wanted to get rid of that. Don't look. Don't look, Maura. You're going to ruin it for everybody. So, Maura's still trying to figure out. All right. Anyway. Okay. Next property of the wave we want to talk about, and I want to tell you about, is wave speed. Okay? So wave speed, by definition, is the speed that a disturbance travels through the medium. So speed that a disturbance travels through the medium. I'm sorry to ruin the surprise for you guys, but I couldn't erase this. It's not erasing for me. So.
What is it ruining?
Well, I'll tell you. Well, I apparently didn't ruin that. So. Yes, sir.
What was number 2 for T?
Energy.
Thanks for paying attention, Trey.
I was.
I see how it is.
Yes, you do see how it is. hopefully you'll see that if you pay attention, you won't miss things on the line. So that's glad we got this on recording today.
I was watching the pendulum. That's why.
All right, watching the pendulum is distracting.
How long does it take for it to stop? Wait, next to they go opposite. It's hard to watch.
It is hard to watch. Actually, it's not hard to watch. It's actually easy to watch. It's much harder to pay attention to these notes.
No, because I like to follow with my eyes, and now it's just like I can't do that.
I know, because you can't, because they don't have the same frequency, right?
Yeah, but still, it's fun to look at because it's just fun to wear until they wear on top of each other like
Now.
what they are right now.
Ooh, they're married. Do you remember when we would swing, and then if you were swinging at the exact same time, you'd be like, we're married, and then when you start going at the different ways, I remember that. Yeah.
Alright, so, let's do this. Alright, to use the pendulum one last time, okay? First, let's go here, okay? And we'll go here. Okay? So, here's what I want you to do. Talk to the person next to you and tell me how the period, frequency, and amplitude of those two pendulums compare to each other. Discuss. Go.
One has a low period. The top one also has a high frequency. High amplitude, low period. High period. That one has a high period. Low. Yeah. The top is high. Has a low period. High period.
Okay, so let's discuss which one has the greater frequency. Top one has greater frequency. Why?
More cycles.
More cycles per second, right? It goes back and forth more times every second, okay? Which one has the greater period? Bottom one, right? Frequency and period are inversely related. Second or third, which one has the greater amplitude? Top. Because amplitude is talking about what? Well, no.
Big energy.
And we're talking about energy in terms of this pendulum. What is the amplitude represented by? How high it goes, right? Or how far it goes, right? The distance that it's traveling, okay? Top one has a big amplitude, even though it has a small period, right? Those two things are completely separate from one another. All right. Next, let's go speed. Like its name suggests, when we talk about wave speed, it's the speed that the disturbance travels through the medium. So wave speed is the speed that a disturbance travels through the medium. Now, when we talk about the speed of something, we need to know two things. When we talk about the speed of anything, not just a wave, but in anything, we need to know two things. What are the two things we need to know to figure something out speed? Time and distance, right? How far does something go? How long does it take to go that far? We have introduced a couple of properties about waves that represent those ideas, right? First, wavelength. Wavelength is a how far, right? Period. Period is a how long, right? So if we take the wavelength and divide it by the period, that will give us the speed. Why? Well, what unit would we use to measure wavelength in? What do we measure lengths in? Meters, right? So this would be like a meters number. And then, period, we would measure in what? Seconds. So we end up with meters over seconds, which is a unit for speed, right? Distance over time. Okay? Catherine, go ahead.
Is the V wavelength?
V is speed, okay? The lambda, remember the upside down y, that's the wavelength, okay? So here, this is wavelength, this is period, which is a time, right? And then this is speed. So V for velocity, that's why. Okay. Very good.
How do you spell lambda?
Lambda, L-A-M-B-D-A. Lambda. All right, but a lot of times, waves are not measured or described by their period. Waves are a lot of times described more by their frequency. Okay? So we learned, right, this little section right here, this expression, this mathematical expression, is exactly the same as this mathematical expression, yes? Right? If we take lambda times it by 1 over t, we'll get lambda over t. But we learned that 1 over t is also how we can express what? The frequency. So we can also calculate the speed of a wave by taking its wavelength and multiplying it by its frequency. We can do wavelength divided by period, distance over time, or we can do wavelength times frequency. Good there? Let's go ahead and, gosh, sorry, buddy. Should have gotten rid of all this stuff. So. Say again? We'll get to that in a second. Let me do this. I'll help you guys out here. Don't sit. There we go.
What if there was just no PowerPoint?
All right, so examples. I know we skipped a line. We'll come back to it. So it says, waves in a pool have a wavelength of 0.20 meters and a frequency of 2.8 hertz. What is the speed of the wave? So we just talked about the idea that to get the speed of a wave, we can calculate it by taking the wavelength times the frequency. Now, from a unit standpoint, mathematically this isn't really hard, right? The wavelength 0.20 meters, and then it tells you that the frequency is 2.8 hertz. Now, mathematically, that's not real difficult, but let's look at it from a unit standpoint, right? Here, this is meters, right? We said that this would be exactly the same as taking 0.20 meters and multiplying it by 2.8 waves for every 1 second, right? That's what frequency is telling us, yes? Yes, no, maybe? All right. So here, if we want to, you can think about putting this over 1 just to turn that sort of into a fraction. That's more your preference mathematically if you want to do that, okay? And then we're just multiplying fractions, so we multiply the tops and the bottoms, right? So 0.2 times 2.8. When you do that, you should get 0.56. Okay? And then from a unit standpoint, you have meters times waves over on the top, and on the bottom, you've got 1 times 1 second. Yes? Anyone see that I just did that? All right. First, waves. Waves really isn't a unit. It's just sort of a counting thing, right? So it's not actually a real unit. So we can just sort of like disregard that. And then we end up with 0.56, but the only units that are left now are what? Meters over seconds, which is what we want because we're trying to calculate speed. Yes? All right, so there's that. Okay. Then, next one says, student moves the end of a slinky back and forth to make waves. Waves travel at 1.8 meters per second and have a wavelength of 1.2 meters. What is the frequency? So here, we know that speed is equal to frequency times wavelength. This question is asking us to solve for what? Frequency, right? So we have to do a little rearranging of this equation to get frequency by itself, right? First, what are you going to do to get frequency by itself? Divide both sides by lambda, right? So you divide this side by lambda, divide this side by lambda. These cancel, and you're left with F equals V over lambda, right? Then you just plug things in, right? It told you that the speed was 1.8 meters per second. It told you that the wavelength was 1.2 meters, okay? And so numerically, we end up with 1.5. What's going to happen to our meters here? They're going to cancel because you got that there and that there, and you're left with 1 over seconds. Okay? It's a seconds, but it's in the denominator. Okay? That's all right. That's what hertz represents. So if you meet units-wise, you're left with 1 over a seconds. We simplify that to 1.5 hertz. Okay?
Wait, why is it at 1?
The one, so, more right here. No, I'm sorry, I should do this. Let me do this. All right, so we've got 1.5 meters over 1 second, yes? That's what the speed is. So you've got that whole quantity over, that's 1.8, right?
Yeah.
Okay, over 1.2 meters, right? Does that make sense what we're doing? This is V is equal, sorry. F is equal to V over lambda, yes. Okay? This is V, this is lambda. Okay? But this is a complex fraction. Right? So the way that we sort of get rid of this would be the same as saying 1.8 meters over 1 second times 1 over 1.2 meters. That's mathematically, those are equivalent, yes?
Okay, yeah.
And so these meters cancel because one's on the top and one's on the bottom, and we're left with then 1.8 over 1 second. Okay? The 1.8 remember we talked about that 1.8, this is really saying 1.8 waves in 1 second, but waves really isn't a unit, you know what I'm saying? It doesn't like show up, it's just a counting thing. So when we end up with seconds on the bottom with nothing, with no other unit on the top, that's the equivalent of 1.8 hertz. Okay. Good there? So we said the other day that mechanical waves are kind of like conduction when we talked about heat transfer, right? It passes energy from one to the next, to the next, to the next. Conditions and states of matter will affect how quickly energy is passed from one part of the medium to the next, to the next, to the next. Which state of matter is going to transfer energy the fastest? We got differing opinions, right? Noor, why did you say gas? Okay, what do the particles in a gas do? They move really fast. They move randomly and they move really, really fast. So that's okay, right? That's an okay guess. But when we look at it, the important thing for conduction to occur is contact, right? How close together are the particles in a solid? Really close. So how quickly are they going to contact one another? Really fast. So the conditions can affect how quickly that wave travels through the different mediums. What we find out is that speed of a wave can change if it enters a new medium, or if the conditions change. Practical example. Andrew, you play cello, right?
Yes.
Okay. Does your cello sound differently when you play it in the wintertime
Yes.
versus playing it in the summertime?
Yeah,
Okay.
it gets out of tune.
Gets out of tune easier, okay? What's different about your cello in the wintertime versus the summertime?
It gets, as I said, it gets out of tune easier because of the cold weather.
Okay, your cello gets colder, right? And it gets warmer in the summer, okay? That affects how quickly the waves travel through the strings, and it also affects how quickly the waves travel through the air. So, Andrew, that affects this quantity in the equation, right? It affects V. If one side of the equation changes, what automatically has to happen to something on the other side? It has to change too, because that's what an equation is, right? If we change one side, the other side has to change. So Andrew, by changing the speed at which those waves travel through the strings of the cello, that changes the frequency of the waves that are created. And then you can adjust that by tuning the strings, right? Okay? But that has to do a lot with the temperature change, okay? Another practical example, marching band, right? So when you guys go outside in the summertime, and then in the wintertime, right towards the end of the season, it doesn't quite sound the same, right? That change in the temperature of the air causes a change in the speed at which those waves travel, and that causes a change in the frequency of those waves. So those are some practical examples of how the speed of a wave can affect things like frequency and wavelength. Okay? Good there. All right. Last thing. Doppler effect. I'm assuming most of you are at least familiar with the term Doppler because you watch TV and you hear the weather report, right? They have Doppler radar, yes? Come on, people.
Who watches the weather? I watch the weather all the time.
People who want to know what's going on outside, Maura.
You can just look on the app on your phone.
I know. Now it's TV. Who needs TV? So, anyway. So So now you can explain Dr. Radar to your grandma now because
Okay.
so anyway, what we find out is that motion can cause a change in the frequency of the waves that you are hearing or that you are perceiving. Motion causes a change in the frequency or the perceived frequency of a wave. Let me do this. I know some of you have started writing it down already, but I'm going to block it. All right. I think I know the answer to this question, but I'll ask anyway. Anybody watch NASCAR or other car racing on TV? No, it does not.
I watched Talladega Nights.
I love Talladega Nights. That's the best
right.
movie ever.
What we find out here, we'll just finish it off real quick. What we find out is that as the distance between the source of the waves and the listener of the waves decreases, we see an increase in the frequency of those waves. If the distance between the source of the waves and the listener is increasing, we see a decrease in frequency. So as things are coming towards you, or as you are coming towards them, they increase in frequency. If you are moving away from them or they're moving away from you, they decrease in frequency. And that can affect their pitch if you're talking about a sound wave, or it can affect other things about how we perceive that wave. On Monday, we start getting into interactions of waves and how they behave when they come in contact with each other or other types of matter. Sorry.
Your pen is